Let's go on an energy adventure. You sat down to do your lesson today and you wrote maybe the title on a sheet of paper. Are you taking notes? You should take notes. Anyway, you wrote down on the sheet of paper something about energy. Where did you get the energy to do that from? Well, if you know anything about biology, it turns out it came from a molecule named ATP. Where did that come from? That one came from your blood sugar. And where did that one come from? I'm guessing you know this one. That came from your food. Maybe you drank some milk before the lesson. Where did the energy in that milk come from? You can keep going with this game, tracing it back and back and back. And the energy in the milk came from a cow, which came from the grass, which came from the sun. The energy from the sun provides almost all of our energy needs here on Earth. If you just think of an energy source, it probably came from the sun. The cool thing is, this teaches us how energy is constantly transformed and reused and repurposed. When we look outside at a green landscape, we're seeing a huge array of self-reproducing, beautiful solar cells, constantly, day and night, collecting energy from the sun. Okay, well, maybe they take the night off, but at least during the day, they collect energy. Let's learn to think more carefully about this energy and all of its transformations. Let's begin by reviewing our lesson objectives. First, we'll introduce energy and work. Then we'll introduce different forms of energy. And lastly, we'll explain simple machines. All right, let's start with energy. Energy is the ability to do work. Okay, well, that can sound sort of abstract, so let's make it concrete and delicious. Chocolate chip cookies. These turn out to carry energy. In fact, you every day deal with units of energy. We call them calories. Each one of these cookies has 230 calories. And if I eat the cookies, then I can go do work because energy is the ability to do work. What sort of work? Well, I could exercise. So I could push this sled with weights on it. That's doing work. So energy is the ability to do work. And one good example of that is food. Of course, there are many others. All right, well, that kind of raises the question, what is work? Work is applying a force across a distance. So you need both force and distance to have work. Here we meet both of those requirements by pushing this sled. Pushing it takes a force, and as long as we're moving the sled across a distance, we have work. It's important to note that if I just lean on the sled and it doesn't move, that actually is not technically work from a physics perspective. Mathematically, work is equal to force times distance. That D stands for distance, and we'll use the units of meters. Whereas F stands for force, and we'll use our standard unit for force here, newtons. Okay, well, if I multiply force in newtons times distance in meters, I'll get my units for work, which is in Newton meters. That's kind of a weird unit, and so what we actually do is we combine Newton meters into one unit. We say 1J, we'll get to what that is equal to 1 Newton meter. Well, a J stands for joules, so work is going to come in joules. And actually, joules is going to be the unit for energy and work. All right, well, now we know what energy and work are. Let's zoom in and think about energy a little more closely. Energy comes in many forms. First up, it comes in kinetic energy. So the bowling ball and these pens have kinetic energy because they're both moving. Kinetic energy is associated with motion. And it's going to depend on mass and velocity. So increasing the velocity increases the kinetic energy, and increasing the mass increases the kinetic energy. But there are other forms of energy that don't depend on motion. Take this slingshot. It's pulled back, and we know this is a high energy arrangement, but it's not moving, at least yet. So potential energy is what we have here, and it's associated with arrangement. Here we specifically have elastic potential energy because we've stretched that band. It's in a higher energy form. But there are many forms of potential energy, including chemical potential energy. So the gasoline we put into our car contains potential energy. Even if it's not moving, it still has a bunch of energy which we can unleash to make our car go. There's also gravitational potential energy, and that's the one we'll take the closest look at in this unit. And that's basically the potential energy you have from being up high. This guy is falling down, so he has kinetic energy because of that motion. But he's going to continue to fall faster because he's still up in the air. So the fact that he's up in the air gives him gravitational potential energy. Now, just because there are many forms of energy doesn't mean they can't be transformed from one type to another. Energy can be transformed from one type to another. Take, for example, this car. Here we took chemical potential energy from the gasoline and turned it into motion. So we took chemical potential energy and turned it into kinetic energy. When we do that, though, energy is conserved. So however much potential energy my gasoline has, that's the maximum amount of kinetic energy I can give my car. Energy is not created or destroyed. That's what we mean when we say energy is conserved. Energy is conserved, but our friend force is a bit more flexible. It's not always conserved. Let's take a look at why that is. Here we have our crowbar prying out a nail. Now, you couldn't pull that nail out directly. Instead, we need the crowbar because it allows us to amplify the force we apply. We call that mechanical advantage. It's a way to amplify force. So going back to our crowbar, we get a really high force on the end attached to the nail, even though we apply a relatively lower force with our hand. How does that work? Where do we get this extra force from? Well, it all has to do with the distance we apply that force over. Notice on the low force side, we have a very long distance over which we can press down the crowbar. Whereas on the high force side, we don't move very far at all. So our crowbar amplifies force at the cost of moving that other end a greater distance. This is an example of a simple machine. Simple machines are just anything that provides a mechanical advantage, anything that amplifies force. Here are a bunch of simple machines, which we'll go through in more detail later in this unit. Pulleys, levers, wheels and axles, wedges, inclined planes, and screws are all examples of simple machines. Let's review what we've learned. First, we introduced energy and work, where we saw that energy was the ability to do work, commonly associated with things like calories, though also joules, and work is just applying a force over a distance. Then we introduced different forms of energy. Kinetic energy, which is associated with motion, and potential energy, which is associated with arrangement. We saw that there are many forms of potential energy. Lastly, we explained simple machines as a way to amplify force. Hey!